Okay, dear students, welcome to physics class of YouTube. So we have been discussing about the chapter here, the electromagnetic induction. So we have covered all the experiments of Faraday and Henry to discuss about the electromagnetic induction, the phenomenon of electromagnetic induction. Whenever the magnetic flux linked with the coil changes and EMF and hence current is induced in the coil. So this phenomenon is called as the electromagnetic induction, right? And we have discussed the Faraday's law of electromagnetic induction, how to calculate the induced EMF and current, and what is Lenz's law we have discussed in the previous sessions. So also we have discussed about the motional EMF and also we have derived the expression for the motional EMF, right? Now the next point here we are going to discuss here is the inductance or the self-induction and mutual induction we have to discuss here, right? One is self-induction and another one is the mutual induction. These 2 points we have to discuss here. So what is meant by self-induction? The phenomenon of induction of EMF in the same coil due to change of flux or the magnetic flux in the same coil. It is called as what here? The self-induction. The phenomenon of induction of EMF in a coil due to the change of magnetic flux linked with the same coil. This is called as what here? The self-induction. Right? What is meant by self-induction? The induction of EMF in a coil due to what? The change of current or the magnetic flux linked with the same coil. This is called as what here? The self-induction. So for this now I will consider here a cylindrical coil. So here is the cylindrical coil we have considered here, right? This is connected to a battery, right? This is connected to a battery. Here is the switch, right? Switch is used here. Through a switch, a cylindrical coil is connected to a battery, right? Now when the key is pressed, when this key is pressed, the current is passed through the coil, right? When the key is pressed, the current is passed through the coil and the current is rises from 0 to maximum, right? In a time, in some time delta t, the current increases. The current increases from 0 to some maximum value, right? As a result, what happens? The magnetic flux linked with the coil also increases from 0 to maximum, right? Now yaವಾಗ key ಅನ್ನು press ಮಾಡ್ತೀವಿ, current increase ಆಗ್ತದ್ರಿ. Current ಜೊತೆಗೆ ಏನಾಗ್ತೈತಿ? The magnetic flux linked with the coil also increases because of what? The magnetic effect of electric current. When a current is passed through a conductor, the magnetic field is produced. Magnetic field means that is a magnetic flux is linked with the coil, right? So when the key is pressed, right, the current increases. With the current, what happens here? The magnetic flux is also increased from 0 to maximum value. Again, what happens? Because of this, whenever the magnetic flux linked with the coil changes, therefore the EMF is induced in this coil. EMF induced at the 3 coil. So this induced EMF opposes the growth of the current in the coil. This is called as what here? The self-induction of the phenomenon of induction of EMF in this coil due to what? The change of current in the same coil. Now we e coil current change e coil EMF induce right? The phenomenon of induction of EMF in a coil due to the change of current in the same coil, and that induced EMF, the induced EMF opposes the growth of the current, right? The induced EMF opposes the growth of the current because of what? Now current change ಮಾಡೋದ್ರಿಂದ ಏನಾಗುತ್ತೆ? EMF induce ಮಾಡ್ತೀವಿ. So according to Lenz's law, that induced EMF opposes the growth of current here. Similarly, when the key is released, so right, when the switch on ಮಾಡಿದಾಗ ಏನಾಗ್ತದೆ? Key close ಮಾಡಿದಾಗ current increase ಆಗ್ತದೆ. ಯಾವಾಗ ನಾವು switch open ಮಾಡ್ತೀವಿ, when the switch is open, right? When the switch is open, current decreases from maximum to 0. Current ಏನಾಗ್ತದೆ ಈ ಕೇಸ್ ಒಳಗ? When the key is released, the current in the coil decreases from maximum to 0. Current decrease ಆಗಕ್ಕೆ start ಆಗ್ತದೆ. So when the current starts to decrease, the magnetic flux linked with the coil also decreases, right? The flux linked with the coil also decreases from maximum to 0. As a result, again the magnetic flux linked with the coil changes and hence EMF is induced in the coil, and this EMF opposes again the decay of current, right? Now key ಕ್ಲೋಸ್ ಮಾಡಿದಾಗ ಕರೆಂಟ್ ಇನ್ಕ್ರೀಸ್ ಆಗ್ತೈತ್ರಿ, ಅವಾಗ ಕಾಯಿಲ್ ಕರೆಂಟ್ ಗ್ರೋತ್ ಆಗೋದನ್ನ ಅಪೋಸ್ ಮಾಡ್ತೈತಿ. ಯಾವಾಗ ನಾವು ಕೀಯನ್ನು ರಿಲೀಸ್ ಮಾಡ್ತೇವೆ ಅವಾಗ ಕರೆಂಟ್ ಡಿಕ್ರೀಸ್ ಆಗ್ತೈತಿ, ಅವಾಗನೂ ಕೂಡ ಏನಾಗ್ತೈತ್ರಿ ಕಾಯಿಲ್ ಕರೆಂಟ್ ಡಿಕೆ ಆಗೋದನ್ನ ಅಪೋಸ್ ಮಾಡ್ತೈತಿ. ಬಿಕಾಸ್ ಆಫ್ ವಾಟ್? ಇನ್ ಬೋತ್ ದ ಕೇಸಸ್ ದ EMF is induced ಡ್ಯೂ ಟು ವಾಟ್? ದ ಚೇಂಜ್ ಆಫ್ ಕರೆಂಟ್, ರೈಟ್? ಕೀ ಕ್ಲೋಸ್ ಮಾಡೋದ್ರಿಂದನೂ ಕರೆಂಟ್ ಚೇಂಜ್ ಮಾಡ್ತೀವಿ, ಕೀ ರಿಲೀಸ್ ಮಾಡೋದ್ರಿಂದ ಕರೆಂಟ್ ಚೇಂಜ್ ಮಾಡ್ತೀವಿ. ಸೊ ಇನ್ ಬೋತ್ ದ ಕೇಸಸ್ ದ EMF is induced due to what? The change of current, right? So the EMF induced due to the change of current. So according to Lenz's law, the induced EMF opposes the growth of current and decay of current. So this phenomenon is called as the self-induction. On the EMF is called as the back EMF. The induced EMF is called as what here? The back EMF. So ಇಲ್ಲಿ ಏನಾಗ್ತದೆ ನೋಡ್ರಿ, as a result what happened? The induced EMF in a coil, the EMF induced in the same coil due to what? The change of current in the same coil. So this phenomenon is known as the self-induction. So self-induction ಅಂದ್ರೆ ಏನ್ರಿ? The induction of EMF in a coil, the induction of EMF in a coil due to change of current in the same coil. Due to change of current in the same coil. So this phenomenon is called as what here? Self-induction. Self-induction ಅಂದ್ರೆ ಏನು? The induction of EMF in a coil due to the change of current in the same coil. This phenomenon is called as what here? Self-induction. And the induced EMF always opposes the growth or decay of current. That means what? The change of current. ಇಲ್ಲಿ ನಾವು current change ಮಾಡೋದನ್ನ induced EMF oppose ಮಾಡ್ತೈತಿ. Therefore the induced EMF is called as the back EMF. Induced EMF is called as what here? The induced EMF is called as back EMF. So why it is called as the back EMF? The induced EMF is called as the back EMF because of what? It always opposes the growth and decay of current in the coil. ಈ ಕಾಯಿಲ್ ಒಳಗೆ ಕರೆಂಟ್ ಇನ್ಕ್ರೀಸ್ ಮಾಡೋದು ಮತ್ತು ಡಿಕ್ರೀಸ್ ಮಾಡೋದನ್ನ ಅಪೋಸ್ ಮಾಡ್ತಿದ್ರು. ಯಾವುದು? ಇಂಡ್ಯೂಸ್ಡ್ EMF. So that's why it is called as the induced EMF is called as back EMF because it opposes the change of current. Change of current means growth of current and decay of current. So this phenomenon is called as what? This induced EMF is called as what? The back EMF, and the induction of EMF in a coil due to change of current in the same coil. So this phenomenon is called as the self-induction, right? So now we have got the definition of what is meant by self-induction. That is what? The induction of EMF in a coil due to change of current in the same coil, right? Now the current, that means what? The magnetic flux linked with the coil at any instant of time is directly proportional to what? The current flowing through the coil. That means what? The magnetic flux linked with the coil, right? That is what? The pi. The value of pi, that is the magnetic flux linked with the coil, at any instant of time is directly proportional to what? The current flowing through the coil at that instant. That means pi is directly proportional to I. Is it right? Right? So current now increase ಮಾಡಿದಾಗ ಏನಾಗ್ತೈತ್ರಿ? The magnetic flux linked with the coil also increases, right? Current increase ಮಾಡಿದಾಗ ಏನಾಗ್ತೈತ್ರಿ? The value of pi, magnetic flux linked with the coil also increases at any instant of time. Now this pi is directly proportional to I, and so the proportionality constant we write here, that is the L, right? This L is called as what here? The coefficient of self-induction. So what we call it as here L, the constant of proportionality. This is called as the coefficient of self-induction, or it is also called as the self-inductance. It is called as what here? The self-inductance, right? L is called as constant of proportionality. It is called as L is constant here, is known as, or it is called as coefficient of self-induction. Coefficient of self-induction, self-inductance, or simply it is called as the self-inductance, right? So this L value, it is a constant, the value of L is constant, it is called as what? It is known as what here? The coefficient of self-inductance, or it is called as simply self-inductance of the coil, or it is also called as self-inductance of the coil. Self-inductance of the coil, it is called as self-inductance of the coil. So current, the magnetic flux through the coil is directly proportional to the current through the coil at any instant of time, or at that instant of time. So as the value of I increases, the magnetic flux linked with the coil also increases here. And now we can write here from the Faraday's second law of electromagnetic induction, E is equal to what? From Faraday's law, from Faraday's law of electromagnetic induction, E is equal to what? E is equal to minus d pi by dt, right? The induced EMF is equal to what? The rate of change of magnetic flux linked with the coil, right? So now let us substitute here the value of pi in this equation. So E is equal to minus d by dt of pi is equal to what? L into I. L into I. Therefore, E is equal to minus L into di by dt, right? So this is what the equation of self-inductance of the coil is. So what we can write from this equation? So induced EMF in a coil is equal to L into di by dt. So induced EMF is depends upon what here, right? Self-inductance of the coil, and it is also depends upon what? The rate of change of current through the coil. So on what factors the induced EMF in a coil depends here? It depends upon self-induction of the coil, and also what? It depends upon what? It depends upon what? The rate of change of current through the coil, right? So self-inductance of a coil, how we can define now self-inductance of the coil? So self-inductance of the coil is numerically equal to what? Is numerically equal to the induced EMF. It is numerically equal to the induced EMF when the rate of change of current through the coil is unity. So yavaga L is equal to E after that is induced EMF, right? So the self-inductance of the coil is numerically equal to, if di by dt is equal to unity or 1, if di by dt is equal to unity or 1, the self-inductance of the coil is numerically equal to the induced EMF. L is equal to what here? Induced EMF when di by dt is equal to unity. The self-inductance of the coil is numerically equal to the induced EMF when the rate of change of current through the coil is unity or 1. Now what is the unit of, what is the SI unit of self-inductance here? The SI unit of self-inductance is Henry. This is also important. So the SI unit of self-inductance, SI unit of self-inductance is Henry. SI unit of self-inductance is Henry or capital H. It is the name of the scientist. The SI unit of self-inductance is Henry, and it is abbreviated as here what? Capital letter H. Right? Now, how to define the self-inductance of the coil here? Right? That is L. How to define here the self-inductance of the coil? L. The self-inductance of the coil is said to be 1 Henry. About the self-inductance of the coil 1 Henry. The self-inductance of the coil is 1 Henry when if 1 volt EMF is induced in the coil and the current change through the coil is 1 ampere per second. So again I will note. So E is equal to, or L is equal to 1 Henry when it is possible if E is equal to 1 volt and di by dt is equal to what? 1 ampere per second. 1 ampere per second. The self inductance of a coil is said to be 1 Henry if 1 volt of EMF is induced in the coil when the rate of change of current through the coil is 1 ampere per second. Right? The self inductance of the coil is said to be 1 Henry if 1 volt of EMF is induced in a coil when the rate of change of current through it is 1 ampere per second. So, one more question they may ask, define 1 Henry. What is the SI unit of Henry? Sorry, what is the SI unit of self inductance? That is Henry, and define 1 Henry. Right? How to define 1 Henry? The self inductance of the coil is said to be 1 Henry if 1 volt of EMF is induced in a coil when the rate of change of current through the coil is 1 ampere per second. So this is the very important term what we have discussed here, the self induction. What is self induction? Right? What is back EMF? Right? From this expression, the magnetic flux linked with the coil is directly proportional to what? The current through the coil. So from this equation we have written pi is equal to L into I. Here L is called as what? L is called as what here? The coefficient of self inductance, or it is called as self inductance. So self inductance of the coil, from the Faraday's law of electromagnetic induction, we have got here the induced EMF in the coil is equal to minus L into di by dt. Here minus N is according to Lenz's law. Right? Here L is called as the self inductance, and the SI unit of self inductance is Henry. And how to define 1 Henry? 1 Henry is equal to what? When the self inductance of the coil is said to be 1 Henry if 1 volt of EMF is induced in the coil when the rate of change of current through the coil is 1 ampere per second. Right? So this is the very important term what we have discussed here, self induction. So next point what we have to discuss here is the self inductance of a long solenoid. We have to take the solenoid and hence we have to derive the expression for the self inductance of a long solenoid. So it is a 2 to 3 step derivation. Now let us do it. Okay, now let us derive your self inductance of a long solenoid. Right? We have considered here a long solenoid of length small letter L is denoted by the small letter L. Right? The length of the solenoid is L, and capital L is what? Capital letter L indicates what? It is the self inductance of the coil, and A is area of cross section of the solenoid. Right? Now let us derive here the expression. L is length of the solenoid. L is length of the solenoid. A is area of cross section. Area of cross section. And small n, just right here, it is the number of turns per unit length of the solenoid. Small n, number of turns per unit length. Right? Number of turns per unit length. And if I is the current flowing through the solenoid, then the magnetic field inside the coil, that can be written here. The expression V is equal to the magnetic field through the solenoid, that can be written here. That means what? When a current is flowing through a solenoid, the magnetic field is produced inside the solenoid. Right? Now, how to calculate that magnetic field? So we have the expression V is equal to mu naught N I, where I is the current through the solenoid, N is the number of turns per unit length, and mu naught is, right? It is the permeability of free space. Right? So V is equal to mu naught N I. Now, from this expression, also as equation 1, the magnetic flux will linked through the what? The coil, that can be written here, or the solenoid, that can be written as what? From the expression pi is equal to BA cos theta. Right? So here theta is equal to 0 degree, cos 0 is 1, so you will write it as what? BA. B into A is equal to what? The magnetic flux linked with the solenoid, it is equal to what? B into A. Right? Here small n, it is what? The number of turns per unit length. So total number of turns, if n, capital letter N is the total number of turns contained in the what solenoid, total number of turns, then what we can write here? So capital letter N is the total number of turns, then small letter n is the number of turns per unit length. So total number of turns n can be written as what here? N is equal to small letter n into L. Right? Therefore, pi is equal to n into B. So let us call this as equation number 3. So this B is what? The magnetic field inside the solenoid. Right? The magnetic field inside the solenoid. And magnetic flux is equal to what? BA cos theta, theta is equal to 0 degree, because of inside the solenoid the magnetic field and the area, right, both are angle between them is 0 degree. So because of what here? See, theta is equal to 0 degree. So we have what here? B into A. So for total number of turns contained in the solenoid, it is equal to NBA. So from these three expressions, what we can write here? B is equal to mu naught Ni. Therefore, pi is equal to what we can write here? This N is equal to what? N into L. N into L. Right? B is equal to what? Mu naught Ni. Mu naught Ni. So finally, what we can write here? And pi is equal to B into A. From this expression only we have written here. So therefore, finally, what we can write here? Mu naught N square, right, and L into I. So this is what the magnetic flux linked with the coil, right, or the magnetic flux inside the solenoid here. So from this expression, what we can write here, and also we know that pi is equal to L into I. That is the magnetic flux linked to the solenoid at any instant of time in terms of self-induction of the coil, self-inductance of the coil, pi is equal to L into I. So comparing these two expressions, right? So in LHS we have pi here, here also we have pi. Now equating the RHS here, it is equal to what? Mu naught N square, L into I. This is equal to L into I. So these two get cancelled, I get cancelled. So L is equal to what? Mu naught N square L. So mu naught N square L. So this is the expression for what here? And one more expression we have to consider here. N, B we have not written here A. So in place of B we have substituted here this mu naught Ni. After that we have A expression here. So this is equal to what? A. And finally what we have to write here? A. So this is equal to what? Mu naught N square L into A. Mu naught N square L into A. Right? So the self-inductance of the long solenoid expression is equal to what? Mu naught N square L into A. Here A is the area of cross section of the solenoid, L is length of the solenoid, and N is the number of turns, right? Number of turns per unit length, and mu naught is equal to what here? The permeability of free space. Now if we replace the solenoid, that means what? If the core of the solenoid used as some other material, then we have to use here the mu naught into mu r expression we have to write there, right? So we have to replace the relative permeability also, right? Therefore L is equal to mu naught N square L into A. It is the expression for what? The self-inductance of a solenoid, long solenoid of length L we have considered. So from this expression on what factors the self-inductance of a solenoid depends here. The self-inductance of a solenoid, it depends upon what? It is directly proportional to the square of the number of turns per unit length, and it is directly proportional to the area of cross section of the solenoid, and it is also depends upon what? If the core contains some other material, we have to consider the relative permeability also, right? So this is the important derivation, right? Self-inductance of the coil, you have to remember this expression on what factor it depends also, right? So this B is equal to what? The magnetic flux inside the magnetic field inside the solenoid. From this expression, magnetic flux we have written here. So from the magnetic flux we have written this expression, and also the magnetic flux from the in terms of self-inductance of the coil L into I. So finally we have arrived this expression here, right? And also the self-inductance. What is the significance of the self-inductance of the coil. So self-inductance, it is called as electrical inertia. So what is inertia? As we have studied in Newton's laws of motion. Inertia ಅಂದ್ರೆ which opposes the change of state, right? Change of state, inertia of direction, inertia of motion, inertia of rest study ಮಾಡಿದ್ವಿ mechanics, right? So similarly here electrical inertia, this self-inductance, it is called as the electrical inertia. So ಅಲ್ಲಿ inertia ಅಂದ್ರೆ ಏನು ಮಾಡ್ತಿದ್ರಿ, it opposes the change of state. So here the self-inductance which opposes the change of current, ಅಂದ್ರೆ ಕರೆಂಟ್ ಇನ್ಕ್ರೀಸ್ ಮಾಡೋದು, ಕರೆಂಟ್ ಡಿಕ್ರೀಸ್ ಮಾಡೋದು, ಅಂದ್ರೆ ಚೇಂಜ್ ಆಫ್ ಕರೆಂಟ್ ಅನ್ನು ಅಪೋಸ್ ಮಾಡ್ತಿತ್ತು. ಅಲ್ಲಿ ಕೂಡ ಇನರ್ಷಿಯಾ ಏನು ಮಾಡ್ತಿದ್ರಿ, ತನ್ನ ಸ್ಟೇಟ್ ಅನ್ನು ಚೇಂಜ್ ಮಾಡೋದನ್ನು ಅಪೋಸ್ ಮಾಡ್ತಿತ್ತು. ಸಿಮಿಲರ್ಲಿ ಹಿಯರ್ ದಿಸ್ self inductance, it also opposes the change of current. So that's why it is called as the electrical inertia. ನಾವು electrical inertia ಅಂತ ಕರಿತೀವಿ. Because of what, right? Mechanics ನಾವು inertia ಅಂತ ಕರಿತೀವಿ, the body which opposes the change of state. So similarly here self inductance which opposes the change of current, therefore it is called as the electrical inertia. So what are the important points what we have discussed in the today's class? What is self inductance? What is self inductance? That means a self induction phenomena, right? Self inductance, that is L. What is the SI unit of self inductance? That is Henry, and how to define it, and the derivation, that is what, the self inductance of a long solenoid. Now in the next video class we will discuss about the next point, that is about what, the mutual inductance and next related properties. Okay, thank you so much.